everyone. Today we're going to talk about solar energy. We're going to start by talking about the significance of the solar energy resource in our energy mix. And then today we're going to dive into solar PV or solar photovoltaics. You all know that solar is the fastest growing electricity resource worldwide. And that's helping us drive down electricity costs. It's helping us decrease the environmental impacts of our energy mix and tackle climate change. And that growth is primarily driven by solar PV. So a reminder from Monday, there are 3 categories of renewable energy resources, and solar fits into the category of the truly renewable energy resource, where use of the resource, or the sun, doesn't deplete the ability of that resource to us. So we've got that big fusion reactor in the sky, and we know that the sun is the source of a lot of our different energy resources, most of our energy resources actually. And today we're going to talk about how we harness that radiant heat and light from the sun directly to produce energy. And we use that solar resource differently, right? It can be very simple, from having a window in your home to let in the light, to something more complex, like having a photovoltaic cell to harness that light resource to generate electricity. I want to do a recap from your assigned videos. There are really 4 different types of ways that we harness the solar resource. The first is indirect use of solar heat and light. It's the simplest and the cheapest method, and it's one that we don't measure, right? It's the mechanisms like having a window to let in light, building thermal mass into your building to capture heat and release it in the evening when you need it. And a lot of measures that would be classified in the energy efficiency category. So it's the most prevalent way that we use the solar resource, but again, it's not really measured, right? Those megawatts. The second method is direct use of solar energy to generate thermal heat. So that's the solar thermal heat. It's this one. And it involves using any simple heat trapping mechanism to transfer heat collected from the sun and use it for heating purposes. Whether you're, in the US, it's primarily used for heating pools. But we've seen more fancy direct solar thermal technologies that even generate steam for enhanced oil recovery in the Middle East. The third method is solar photovoltaic that generates electricity from sunlight by wiring semiconductor material together in a circuit that can generate a current when they're hit by photons from the sun. And then the fourth method is that solar thermal electric, or concentrating solar power, CSP, that Diana talked about in the assigned videos, where CSP uses mirrors or reflectors to reflect light onto and concentrate it onto receivers that convert that collected solar energy into heat, and that heat can be used to make steam that spins a turbine to generate electricity using that steam cycle, the traditional way that many of our power plants generate electricity today. I think you heard from Diana that CSP is largely experiencing very limited growth today because of the relative economics. It's rather expensive to do. Let's talk at a high level about the economics of different solar electricity generation resources. Again, this is the LCOE chart. It's from last year because it's got rooftop solar on this, but you can see that solar electricity generation resources make up some of the most expensive electricity that we're building today, and some of the cheapest. So with rooftop solar being the most expensive, utility scale solar being the cheapest. CSP isn't on this chart because we aren't building any new projects today in the United States, but if it were, it'd be pretty expensive as well. So we'll come back to this topic of economics later on in the class. But as we talked about before, solar is a relatively small portion of our energy mix. It's becoming more and more significant in our electricity mix, but it is the fastest growing energy resource worldwide. Here you see global growth trends of different electricity or energy resources, excuse me. And on the right here, you've got the growth of solar in the US electricity mix broken out by large scale, small scale, and concentrating solar power. So you can see CSP is a really small sliver there, and the bulk of our solar generation in the US is large scale. And again, solar has been the largest electricity resource to be built on the grid in terms of new power generation. That's what this is showing you here, along with wind and batteries, and to a lesser extent, natural gas. And it's, again, one of those resources that has overshot expectations. As you can recall from this IEA chart that shows IEA's and forecasts for solar capacity additions over time and what's actually happened globally with those solar capacity additions. So IEA and many continue to underestimate the potential for change. And although we're certainly going to see short-term impacts from changes in tax credits and other incentives that have happened as a result of HR1, over the long term, the fundamental economics and competitiveness of solar are going to continue to drive this growth. I've been working in the renewable energy industry for quite a long time and seen a lot of changes, lived through a lot of changes in the tax credits. And I think often you'll see, or you'll hear folks say, "Oh, this is the end of solar. This isn't going to continue." But that's really short-sighted and not recognizing again those economic forces and market forces that will continue to drive this growth, both in the US and worldwide. The solar resource is large, to say the least. We barely put a dent in the resource that's available to us. Again, this depicts the economically recoverable resource worldwide of different energy resources, with your stock resources on the left and your flow resources on the right, which show what's available annually. In the context of the US, we have sufficient technically recoverable solar resource to meet our electricity needs 75 times over. So let's talk about how we characterize that resource. The solar resource, it's available almost everywhere. Certainly there are areas in the world like Northern Australia or the Southwest that have more solar resource than other areas, but we can pretty much economically build a solar project almost anywhere, from Alaska to the Northwest, to Maine and the Northeast. As long as you have somewhere to send that electricity to, right? You either need to be close to load, to demand centers, or have sufficient transmission capacity to transmit the electricity to demand centers. So a few important terms that I want you to know about related to the solar resource. The solar resource can be measured in terms of irradiance, which is the amount of energy that hits a particular surface area when the sun is at a 90-degree angle to the Earth. So irradiance is measured in watts per meter squared. And the chart, the map that you see here on the left is showing irradiance worldwide. The solar resource can also be measured in terms of insolation, which is the amount of energy that hits a particular surface area over a given time frame, like throughout the day. So this map here from NREL, it shows solar insolation in terms of kilowatt hours per meter squared per day, right? Because the solar resource is going to vary as the sun moves throughout the sky. So two more terms I want you to know about with regards to the solar resource. You've got both diffuse and direct radiation. Direct radiation is solar radiation that travels in a straight line from the sun to the Earth without being disrupted or scattered by particles in the atmosphere, whether it be clouds or pollution and whatnot. And diffuse radiation is radiation that is disrupted by particles in the atmosphere. So in the middle of a clear sunny day, the direct radiation is about 85% of solar radiation that hits the ground. But on a completely overcast day, you've got 100% diffuse radiation. And this is important because different solar technologies have vary in terms of whether or not they can take advantage of diffuse radiation. Anything that uses reflectors can't take advantage of diffuse radiation. And that's why you see a lot of the concentrating solar power projects built out in the middle of the desert that has the most direct radiation, right? You don't have a lot of cloud coverage in the desert. Solar PV, for example, can take advantage of both direct and diffuse radiation. All right, so that's the solar resource. Let's transition to talking about solar PV or solar photovoltaics. There are a variety of different formulations of the solar PV technology. You can have different semiconductor materials. There are different device types, different structures that hold the panels. And what you choose is likely going to depend on your application. For example, the early applications for solar PV were in the space industry, where you needed to get power on your satellites and probes, and there's limited surface area on those satellites and probes. So what they would do is they would use the solar PV technology, and they would use the most efficient ones as well, because they want to increase power output per unit of surface area. Another early market for solar PV was off-grid applications. So probably about 3 or so decades ago, we only really saw solar PV in off-grid applications that otherwise had overly costly grid interconnection alternatives. And it's really only been in the last 3 decades that we've seen on-grid applications take off. PV photovoltaics, it uses energy from sunlight to move electrons around in semiconductor materials in a controlled manner in order to generate a current. So there are certain materials that exhibit a characteristic known as the photoelectric effect that causes them to emit electrons when they're hit by photons. So these are semiconductor materials. And what a PV panel does is it puts 2 layers of semiconductor materials together that each have different types of impurities introduced into them, which is a process called doping. So one layer of the material is doped to have a spare electron, and this is the negative type or the N-type layer. And the other layer has a missing electron. This is the positive or the P-type layer. And the boundary or interface between those 2 layers is called the p-n junction. So when photons from sunlight strike the PV panel, electrons are knocked loose from the atoms in the semiconductor material. And if electrical conductors are connecting the P and the N type layers, then that forms a circuit, and the flow of electrons through that circuit can generate electricity. And this process generates direct current, right, which is different than most other thermoelectric power plants that generate AC power. The solar cell is the basic building block of a solar PV system. So an individual PV cell, it's small, as you can see, it's about 4 inches across, and it can typically produce between 1 and 2 watts of power. To obtain a useful voltage, you wire those cells together in series in order to form larger modules or panels. And modules can have hundreds of cells wired together, to have a power output of anywhere between 300 watts to up to 600 watts. So these panels and modules can be quite large. And modules, they can be connected together to form arrays. One of the things that's really important to know about solar panels is the power output from a given module or modules wired together in series is limited by the current produced by the least efficient cell. So that means that if you have a portion of your module or array that's wired in series that's shaded or that's dirty, it's going to reduce the power output in that entire array that's if it's wired in series. It's, we like to use the water analogies here in this class. If you get a clog in your pipe, it's going to reduce the water flow through the rest of your pipe. And this is one of the reasons why, as we talked about earlier, consideration of shading at your site when you're building a project is really important. If you have mountains next to your project, or you've got trees, or even if you're placing your arrays too close to each other, they could shade each other, right? And significantly reduce the power output of your project. Okay, so let's talk about the different types of semiconductor materials. You've got a variety of different materials that you can use, but the most common one that's used is silicon, used in 97.7% of applications. And you've really got two types, monocrystalline silicon and polycrystalline silicon. As you can see here, we used to do make some polycrystalline silicon in the world, but largely we're just making monocrystalline silicon. So monocrystalline silicon is grown as a large single crystal, otherwise known as an ingot. I think this is a chip off of a bigger ingot. There are some really cool YouTube videos where you can see these things being kind of grown, and then they're sliced into really thin layers to make the semiconductor material for the cell, otherwise known as wafers. And polycrystalline silicon is made by casting silicon in blocks or growing it as a thin ribbon. Monocrystalline silicon has higher efficiency because it is that single kind of pure crystalline structure. But polycrystalline silicon is easier to manufacture, it's less expensive. But despite that, the efficiency gains of mono are preferable, and that's why we build it that's why it's the one that's primarily produced. So you've got the silicon technologies, semiconductors. You also have a broad category of semiconductors known as thin film, which refers to how the material is manufactured and the resulting thickness of that material. So thin film semiconductors, they can use a variety of different materials, SIGs, they can use amorphous silicon, but the primary material that's used today and makes up 2.3% of production is cadmium telluride, or CadTel. And the primary entity that manufactures those panels is First Solar. So there are a variety of different factors that might cause you to pick one semiconductor material over the other. One is cost to manufacture. Other considerations are things like temperature sensitivity or degradation of power output over time. But a really significant consideration is going to be efficiency. So this chart is from NREL. It shows the efficiencies of different semiconductor materials achieved in the lab over time as research and innovation has occurred. And it's important to keep in mind that efficiencies in the lab are going to be higher than efficiencies that you experience out in the real world. I'll talk more about that in a minute. But monocrystalline silicon and polycrystalline silicon, again, they're the most prevalent worldwide. They're the ones in blue here. You can see the crystalline silicon cells. They've got efficiencies ranging between 21% and 28%. These are two materials, they don't necessarily have the highest efficiencies, as you can see here, but they strike that right balance between cost to manufacture and efficiency. Cadmium telluride is in green with the yellow filling, and you can see that CadTel has benefited from some pretty significant efficiency gains, much more accelerated than the crystalline silicon cells, to the point where they're at 23% efficiency, rivaling that of crystalline silicon. So the max theoretical efficiency of a single junction solar PV cell is 33.7%. But you can see here that several of the technologies of semiconductors in purple have achieved efficiencies greater than that. And that's because these are what are called multi-junction cells, which are made up of multi-semiconductor materials stacked on top of each other with multiple PN junctions. And to understand these these semiconductors, multi-junction cells, it's important to understand that different semiconductor materials and PN junctions have different band gaps, which is the minimum amount of energy required to lock or knock an electron free of its bound state. So the different wavelengths of sunlight have photons with different amounts of energy. So multi-junction cells allow the PV panels to take advantage of a much broader spectrum of sunlight. Multi-junction cells, though they're more expensive, so they're only used in applications where there's a high premium on efficiency, like in those space applications that I was talking about. Another method for increasing efficiency is through concentrating, using reflectors to concentrate light onto your PV panels. So that would be the blue square that's empty in the middle. So you can get increased efficiencies, but typically the additional costs and the maintenance of all those moving parts with the mirrors and the fact that you can't take advantage of diffuse radiation with the reflectors don't outweigh the benefits and the productivity increase, the efficiency increase. So we don't see a lot of concentrating photovoltaics being built today. I think there's maybe one at the radio station, on the Dumbarton as you're crossing that bridge, if you want to keep an eye out for it the next time you're there. Okay, and then you've got an emerging PV technology. I'll call out perovskite cells, which is the kind of red-orange filled with yellow. Perovskite cells were really discovered in, I think, 2008, 2009 timeframe. And they're still in R&D phase, but there's a lot of excitement around them because they've achieved such significant efficiency gains. They've gone from, I think, 14% efficiency to over 25% efficiency in less than a decade. Something that took crystalline silicon cells decades in order to achieve. 60 years, actually. So the term perovskite refers to the crystalline structure of these cells, and they can be made from fairly readily available industrial materials. But the challenge with perovskite cells is that they tend to degrade pretty quickly when they're exposed to sunlight, to high temperatures, and moisture as well. So most of the R&D efforts are trying to figure out how to reduce those degradation rates. All right, and as we talked about earlier, another big innovation that's happened just in the past few years has been the growth in bifacial solar technology, where you're putting the solar technology on the back of solar panels, also known as PERC technology. And bifacial PERC can increase the productivity, and that allows the panels to take advantage of reflected and refracted light that bounces off the ground, and can increase the productivity of your PV panel by between 10 and 15%. So this is another great example of how innovation can continue to help costs decline and productivity increase in making the economics of these projects work. So let's talk about what affects the capacity of your PV panel. The minimum power output of a PV panel is typically measured under what are called standard test conditions, which is at 25 degrees Celsius when at an irradiance of 1,000 watts per meter squared, which is basically when the sun is at a 90 degree angle to the equator. And with an air mass of 1.5, which means it's a pretty clear day. There's not a lot of particles in the air to disrupt that light. In reality, though, out in the field, solar projects don't experience standard test conditions normally, right? 25 degrees Celsius is about 77 degrees Fahrenheit. You can imagine in the desert, solar panels are operating at much higher temperatures. And not all solar panels are at the equator at noon. So solar capacity is often given in DC under these standard test conditions. But in addition to standard test conditions not being the norm, it's also important to understand that our grid runs on AC, so Most other power plant capacity is given in AC and accounts for those inverter losses. So if you see solar capacity given in AC, that means that it's typically 20 to 25% lower capacity than its DC rating. It also means that the AC rating is typically under what are called performance test conditions, which are much more reflective of the conditions under which solar projects are operating. So it's something really to keep in mind. You know, oftentimes when you're looking at Wood Mac or Green Tech Media data on solar capacity, they're providing it in DC. And I've seen folks make the mistake of comparing that to other power data provided in AC without making that conversion. Another thing to keep in mind is that solar PV panels, they experience a slight degradation over time. And some semiconductor materials degrade faster than others, like multicrystalline silicon, as you see here. It's not really well understood why, but there is some ongoing research around the factors that go into this. But if you're modeling out your project economics and your productivity over a 20-year lifespan, you have to take into account this degradation. Okay, so we talked about PV materials and panels, and in addition to the panels, there are what are called the balance of system components that include all the non-module components like the racking system, which is the structure that holds the panels. You've got your inverter and the fuses and the cutoff switches as well. In terms of the structure that holds your panels, you can have a few different types. Your structure could be fixed, so your panels are only facing one direction or one angle. Or you could have a structure that allows the panels to track the sun throughout the day. You could have a single axis tracker that allows your panels to track the sun in two directions. Or you could have a dual axis tracker that allows your panels to track the sun in any direction, basically. Your single axis tracker has a productivity boost over your fixed tilt systems of about 25 to 35%. The double axis tracker boosts that another 10 to 15%. Most of the time, we don't see a lot of double axis tracking, dual axis tracking out in the field because the additional costs of those moving parts doesn't really isn't really offset by the productivity gains. But most utility scale solar projects you'll see have single axis tracking in order to take advantage of that productivity boost. All right, so let's talk about the solar industry and kind of growth trends in that solar industry. Can't say it enough, solar is growing really quickly. China is the leader in solar growth, although early days of the solar industry, actually Germany was the leader. You wouldn't necessarily expect that, but they made a big investment in their, in particular, rooftop solar through a feed-in tariff. But in 2015, China surpassed Germany as the world leader. So that showed capacity additions. Here we're looking at where PV modules are produced and manufactured. Again, in the early days, in 2005, PV manufacturing was concentrated in Germany and the US and Japan. But since then, we've seen China make huge investments in their domestic solar PV manufacturing industry. And the result has been that much of PV manufacturing is concentrated in China and in Southeast Asia. You can see over here, in terms of the companies that manufacture these, at least half of them are based in China. You've got, First Solar, that's a US-based manufacturer, but most of their manufacturing capacity is actually in Malaysia. You've got Canadian Solar, again, headquartered in Canada, but most of their manufacturing capacity is in China. And you can imagine that because of this, solar manufacturing gets caught up in a lot of the trade wars with China. So as a result, in 2018, President Trump put in place a tariff on PV cells manufactured in China, and that's something that was extended under Biden. And the Inflation Reduction Act in particular made a huge investment in domestic clean energy manufacturing capacity, including for solar PV. So we have seen some reshoring of solar PV manufacturing capacity here in the US as a result of that. Okay, so we were looking at global data there from both capacity and manufacturing standpoint. Let's zoom into the US, and this chart shows you US capacity additions both historically. Sorry, this should be one over. This is historical, and then this is forecast. And you can see a pretty significant dip in forecast capacity additions as a result of the changes to tax credits that we were talking about earlier. Tax credits are a huge driver of solar capacity additions, but so are other policies like renewable portfolio standards, PURPA, as we talked about before in this class, renewable energy certificates, and a big one is going to be net energy metering, which is something that is typically implemented at the utility level and either required by policy or by public utilities commissions, where utilities are required to buy solar power produced by rooftop solar projects by individual customers. And of course, one of the challenges of this growth in solar energy is the significant ramping requirements that integrating more and more solar places on the grid, something that, as we've talked about many times in this class, is depicted by the so-called duck curve. And again, as we've talked about and as you learned in your local field trips, solar provides a lot of the electricity needs of Stanford, primarily through two large utility-scale solar projects located in Central California. But there's also, as you walk around campus, you probably noticed that a lot of buildings also have some rooftop solar. All right, I'm gonna, given time, skip through these and really quickly just say, there are a lot of, I've heard a lot of myths about the environmental impacts of solar projects, including that it takes more energy to make them than they produce. Something that countless studies have showed is very much not true. The electricity produced by most solar projects is like 20 times more than the energy required to make it. Also, a big rumor that I hear quite often is that solar PV projects take a lot more land than, say, their fossil fuel counterparts, which might be true for the actual power plant itself, but isn't true if you're thinking about the land needed for resource extraction for fossil fuels. And I wanted to end by talking about economics, and in particular, why we see such a huge cost differential between utility scale and rooftop solar. And if this cost differential exists, why do we still build it? And ultimately, it comes down to the fact that we've got a big subsidy in the form of net energy metering, where rooftop solar projects are getting the retail rate for electricity rather than the wholesale rate, which, as you all know, as we've talked about before in this class, the retail rate is not just about the generation of electricity, it's also about the reliable delivery of that electricity through the transmission and distribution system. So net energy metering, if it's providing the retail rate for distributed solar, it's a significant subsidy where those distributed solar customers aren't necessarily paying for the use of the grid, which, if they're exporting solar power onto the grid, it means they're using the grid effectively as an energy storage facility. So this dynamic of utilities not being able to recover their full costs has resulted in people talking about the utility death spiral, and is the reason why we see a lot of changes in utility rate designs around net energy metering. And if you guys have been following it in California, there have been huge wars around changing net energy metering in order to kind of correct this inequitable subsidy. So thank you all. I appreciate it.
If you want to learn more about this topic or other energy topics, visit our Stanford Understand Energy Learning Hub for free resources, including signing up for our monthly Energy Spotlight. Don't forget to subscribe to our YouTube channel and tap the notification bell to be notified for our newest content.